Still spamming carboxylic acids. I can do something now. Do I really need loopback? I don't think I need loopback. Pop out the chat. Okay. All right. Whatever. You know. Whatever. Did I do this synthesis of? Oh, this is gonna drive me fucking. Did I do this? Write the mechanism of the reaction shown to do this. Okay, wait. Let me think about what happened. I'm pretty sure this is a pretty simple reaction. I think this just goes in, comes out. I think it's that simple. But then the only other thing is that the Cl minus then goes towards. Oh, boring. You know what? You should have never dropped the class because we're having a great time. Should have never dropped the class, and I'm watching the chat. And now there's some random guy. We could have been lab partners. It's also not boring. We made benzocaine. Okay, we made benzocaine, and then we snorted a line of it in class. We made this topical anesthetic in class, and then we... That's what we did in class. Let me look at the answer. So this was 11. But it is like 8:30 every morning, so it is like kind of a slog actually. I mean, I'm glad I'm in it, but it's like every day. So it's just like chemistry all the time. Chad Miller is good. He's actually so much better than Artoon at lecture. Holy cow, I forgot what it was like to actually listen in chemistry. I don't think I listened to her once all quarter. Chad, he's got me locked in. He's telling a story. I mean, she's the best. She's nice. But and her class was easy. Chad is crazy. I think he's on something. Like the way his mannerisms, he's so like, like he's so geeked. I don't know what's going on with Chad, but I think he is a little crazy. Like when he was doing chemistry or something, like he inhaled some fumes or something. Okay, so this is basically exactly what I thought it was going to be. Oh, I got all these right. Okay. He does, because the thing is, he looks around the room and then he like stare at you really intensely, and you can't help but notice his like freaky, soul-piercing eyes. You'll never forget him. Once you're in class and you think he's gonna call on you or something and stare at you, you'll never forget it. All right. See ya. I gotta study. Okay, here we go. Conversion of acid chlorides into alcohols. Reduction in Grignard. Acid chlorides can be reduced by LAH, real primary alcohols. Um, the reaction is a little, however, because parent carboxylic acid are generally. Okay, yeah. So it's just like, okay, a cheaper route would just be by the CA. Reduction occurs via typical nucleophilic ACL substitution mechanism in which a hydride ion adds to the carbonyl group, yielding a tetrahedral intermediate that expels Cl minus. The net effect is the substitution of Cl by H to yield an aldehyde, which is then further reduced by LH in a second step to yield the primary alcohol. Grignard reagents can react with acid chlorides to yield tertiary alcohols. Tertiary alcohol? Oh, yeah. Okay. Oh, yeah, with two identical substituents. The mechanism of the reaction is similar to that of LAH reduction. First, adds expels, but then the carbonyl is reformed, and then adds, and then you protonate. Okay, that's pretty simple. All right, here, this is the one that I didn't know. Conversion of acid chlorides into ketones. Diorganocopper reaction. The ketone intermediate formed in the reaction of an acid chloride with a Grignard reagent can't usually be isolated because addition of the second equivalent of it happens too quickly. The ketone can, however, be isolated from the reaction of an acid chloride with the lithium diorganocopper Gilman reagent. The reaction occurs by initial nucleophilic ACL substitution on the acid chloride. What is this mechanism? Oh, this is more general than they give it credit for. Is there a mechanism? But this is not. I'm specifically curious about uh, on the substitution reaction part. Oh no, this is just all of chemistry. Wait, actually, let's see if there's a mechanism for carboxylic acid ketone formation. Sort of find I'm not curious about the coupling reactions. I'm specifically curious about mm, I do not remember this Gilman stuff at all. Okay, fine. I'm not gonna even bother with the mechanism of this one. So there's just one of these special ones where if we have R prime 2 CuLi in like ether, then we're gonna get first R C double bond O, then it's gonna go to Cu R prime, and then that's the intermediate, and it goes to R C R prime. All right. Oh, minus 78 degrees. And yields are often excellent. Oh, yeah, it is E. Oh, yeah. Okay, okay. benzoic acid, and then you would just do, well, actually, hold on. So we're trying to synthesize. And this should be called, what do you call this? I don't know about these ketones. One phenyl, two methyl, prop one one. One phenyl, one phenyl, two methyl. There should really be two methyl, one phenyl. Two methyl, one phenyl, propan one one. Okay, and to synthesize this, oh, actually, we could just do Cu, I don't know, Li, and then we have isopropyl group, isopropyl group. Okay, the other one, I think you could do it either way, right? You could either start with this acetic acid or carboxylic acid, and then you could just have the Cu double bonded to propyl groups, or you could have like butyric acid. Yeah. All right. Let's see what the answer is, because I think, yeah, you could either do this. Oh yeah, I forgot that it's you have to react it not with the carboxylic acid, but you have to add. So this would be called benzoyl chloride. And this would be called like 2-methyl propanoyl chloride. Or wait, no, 3-methyl butanoyl chloride or something like that. Okay, acid anhydrides. Acid anhydrides are typically prepared by nucleophilic acyl substitution reaction of an acid chloride with a carboxylate anion. As we saw in the previous section, both symmetrical and unsymmetrical acid anhydrides can be prepared this way. So acid anhydrides can do a lot of the same chemistry as the Oh yeah, here you go. The chemistry of acid anhydrides is similar to that of acid chlorides. Although anhydrides react more slowly. Oh wait, don't we have a reactivity ranking? It might not be in these notes. No, here we go. Yeah, anhydrides are second. They're not as reactive, but they're the second most reactive of the carboxylic acid derivatives. Acid anhydrides react with water to form acids, with alcohols to form esters, with amines to form amides, with LAH to form primary alcohols. Only the ester and amide forming reactions are commonly used, however. No, but I actually wanted to use acetic anhydride to make the banana molecule because less water. All right, here we go. Oh, no way. Aspirin synthesis. Oh, shit. Why doesn't it add to the other alcohol? That's what I don't understand. Acetic anhydride is often used to prepare acetate esters from alcohols. Is prepared commercially by the acetylation of orthohydroxybenzoic acid with acetic anhydride. It's crazy that that's all aspirin is. Okay, conversion of acid anhydrides to amides. Acetic anhydride is also used for N-substituted acetamides from amines. For example, acetaminophen, a drug used in over-the-counter analgesics like Tylenol, is prepared by reaction of para-hydroxyaniline with acetic anhydride. Only the more nucleophilic NH2 group reacts rather than the less nucleophilic OH group. Dude, that's Tylenol? Okay, wait. First off, let me just say aspirin. So, salicylic acid, which is orthohydroxybenzoic, with acetic anhydride. So first, okay, so that was the. Oh, that's where it went wrong. Okay, I can do it better. So this is aspirin or acetyl salicylic acid. Okay, we can make amides with anhydrides. Right? That's what it's showing? And making Tylenol is one example. Presumably you don't need I'm kind of curious. Has anyone made Tylenol? This is a pretty simple reaction. The only thing is that dude, of course now Red did it. He actually turned aspirin Wait, he turned aspirin into okay, so first let me get this reaction and I want to understand what he did. Because that's sick. So here we go. So we have 4-hydroxy aniline. And then we have acetic anhydride. And so what's going to happen is so this is Tylenol. Dude, I actually kind of want to do this reaction. That sounds sweet. Let's just see if there's a diagram. Um, how does he do it? Oh, here we go. Oh, wow. So he has to. I've never done a nitration reaction. Does he explain it in more detail? I feel like he never goes into enough detail. He's trying to make it so general audience that it's not good enough. So I don't know anything about removing an acetyl group. Deacetylation. And then decarboxylation. How does he do it, bro? This is actually so nice because then I don't have to watch the video like on stream. The thing is, genuinely, this is like the worst. It's like actually so bad. Like you, I don't know. It's like like whatever prompt they put in is like so insane. It's gonna say the video did not dude. I mean, it's just like so bad. Dude, that's what I'm saying. Is like for some reason, whoever's at YouTube is like you are only allowed to talk about the video. Like I don't know what the problem is, but it's just so bad. It's just so bad. Oh my god. I don't know who thought that was a good idea, but like it's just like so brain dead. But why did he use a coffee grinder? I mean, like, piss me off, dude. Actually pissing me off. Anyways, that's pretty cool that you can turn. So the way that he did it to go from aspirin to Tylenol was aspirin, uh, oh, and then he turns that into salicylic acid. Then he turns that into phenol. And I guess plus CO2, right? I don't know what is the byproduct here? Is the byproduct ethanol? What is ethanol again? Acetaldehyde. Um, and then he nitrates it, which we really did not get into enough. I need to like review that. But you add an NO2 group, and then you on the and somehow I don't know about these directing effects enough to know why doing these additions to the ring, how you can specifically get it on the para position. But then he forms para um, hydroxyaniline. And then once he has the aniline, he reacts it with. He probably reacts it with. Oh, he did. He used acetic anhydride. Dude, this video rules. That is so cool. Dude, we made benzocaine in class today. But this is awesome. What a cool synthesis. I don't know this step. He just uses sodium borohydride. So sodium borohydride can reduce nitro groups. I hate this thing. I hate why it's so stupid. Who's ever behind this thing is just like so. Oh, it gets me worked up because it's like it could be so useful, and then they just make it stupid. They make it like aggressively stupid. Okay. Notice in both of the previous reactions that only half of the anhydride molecule is used, while the other acts as the leaving group during the nucleophilic acyl substitution step and produces an acetate ion as a byproduct. Thus, anhydrides are inefficient and acid chlorides are normally preferred for introducing acyl substituents other than acetyl groups. Write the mechanism of the reaction between parahydroxyaniline and acetic anhydride to pair the acetum. Alright, I already did that. It's so obvious. Yeah, in, up, deprotonate, down, and out. So you get our carboxylate ion and then Tylenol. Oh, acid or ace acid for acetyl, amino, fen for phenol. Bro, acetaminophen. Acetaminophen. That's, or fen. Acetaminophen. That's fun. I actually understand that name now. But I feel like it's a marketing name. It's not really like a real name. But okay, so that was easy. What product would you expect from the reaction of one equivalent of methanol with a cyclic anhydride like phthalic anhydride? Whoa. Okay, wait. Actually, this is pretty interesting. Fuck. I guess it gets pertinent. Oh, wait. Uh, or it's, what am I doing? Okay. All right, the chemistry of esters. Esters are among the most widespread of all naturally occurring compounds. Many simple esters are pleasant smelling liquids that are responsible for the fragrant odors of fruits and flowers. For example, methyl butanoate. I want to do that one. I actually have the butyric acid, I've got the acid, and I've got the methanol. I got a bunch of methanol found in pineapple oil. Isopentyl acetate is a constituent of banana oil. I already made that. The ester linkage is also present in animal fats and many biologically important molecules. So I want to make this. I remember making this, but at the time I didn't know any chemistry, really. The chemical industry uses esters for a variety of purposes. Ethyl acetate, for instance, is a commonly used solvent. Dialkyl phthalates are used as plasticizers to keep polymers from becoming brittle. You may be aware that there is a current concern about the possible toxicity of phthalates at high concentration, although a recent assessment found the risk to be minimal. Dibutyl phthalate. Oh, interesting. Oh. It's so cool learning OChem though, because you can now look at a molecule and you just like I think some people like your whole you look at a molecule and now you just understand so much more just by looking, like so much information is present in this. All right, preparation of esters. Esters are usually prepared from carboxylic acids by the methods already discussed. Thus, carboxylic acids are converted directly into esters by SN2 reaction of a carboxylate ion with a primary alkyl halide. What is the mechanism there? So we can do this. I've never done this esterification before. I've only ever done Fischer. Reaction of esters. Esters undergo the same kinds of reactions that we've seen for other carboxylic acid derivatives, but they are less reactive toward nucleophiles than either acid chlorides or anhydrides. Yeah, so the order acid chlorides, anhydrides, esters. All their reactions are applicable to both acyclic and cyclic esters called lactones. My favorite reactions by far are intramolecular reactions. I find intramolecular reactions really interesting. Because like the thing that is not emphasized enough in organic chemistry is just how dynamic these molecules are. Like let's just see. How big is your brain? Oh, wait. I don't know if I'm allowed to do that. Do they actually? Do they have a? They don't really have AI search. It's kind of interesting. How big is your brain? I'll tell you my mind is. I wanna know how open your mind is. Pain. How do you feel about timing? Bro, this is not. Does this have any?
Oh,
Bro, there really is not good videos, man. Bro, please not this fucking guy. Dude, nobody. There has to be like a video of someone simulating like a really long chain alkane and watching it go like this. Like I feel like I've seen it before. That's what's pissing me off. Whatever. Lactones, cyclic esters. There's two things that are almost always worth doing in chemistry on the paper: resonance forms and rotating about the sigma bond. That is probably the most useful thing. For real. Alright. Conversion of esters into carboxylic acids by hydrolysis. An ester is hydrolyzed. Oh, they actually say that water takes that proton, which then ester hydrolysis is common in biological chemistry, particularly in the digestion of dietary fats and oils. We'll save a complete discussion of the mechanistic details of fat hydrolysis until 29.2. But we'll note for now that the reaction is catalyzed by various lipase enzymes. It involves two sequential nucleophilic acyl substitution reactions. The first is a transesterification. Oh, I forgot about the transesterification. There's something weird there, but something happens. Okay, I don't really know what's going on. Why is saponification irreversible? Whatever it is, it has to do with the fact that for some reason, carboxylic acids don't add. Wait, I actually don't know. Hmm. All right, more ester chemistry. It's so funny. I remember doing this stream where I looked through all of the functional groups like at the beginning of the year, and I was like trying to remember, is ether ester? I can't remember the difference now, bro. It's not like it's just so embedded. There's no way I could ever mix those two up. Esters react with ammonia and amines. Okay, ammonia and amines yield amides. The reaction is not often used, however, because it's usually easier to prepare an amide by starting with an acid chloride. Okay. Yeah, this nucleophilic acyl substitution thing is pretty powerful. All right, alcohols. Esters are easily reduced by treatment with LAH. Diisobutyl, diisobutyl aluminum hydride. Such partial reductions of carboxylic acid derivatives to aldehydes also occur in numerous biological pathways, although the substrate is either a thioester or an acyl phosphate rather than an ester. Butyrolactone. What a weird name. What's the real name for this? I think with LAH you got a diol. And with diba, we should get how do we name aldehydes? It's gonna be 4-hydroxybutanol. Let's make sure I got it right though. Good. Two methyl, one pentanol. And then B, here we have phenyl. What is this called? This should be called phenyl benzoate, right? Boom! I'm so good at this. So here, show the product. We should get okay, good. Benzyl alcohol. That's a weird ass name. Can we get the real name benzyl alcohol? Oh, yeah, dude. Why does PubChem not have any? I don't really get that name, to be quite honest. But okay. All right, conversion of esters into alcohols by the Grignard. Yeah, okay. I actually like this one because this is one that's like pretty fun. All right, so we did this in lab. So ester to all with Grignard. Grignard. I'm actually gonna bring back Grignard. That Grignard reagent. Because, what's up with the French? All right, so we have methyl benzoate. And we're reacting it with phenylmagnesium bromide. And then finally H3O. Okay, so what happens here is this is a minus, this is a plus, basically. This goes here. So first, it's just a cool reaction. What ester and what Grignard might you start with to prepare the following alcohol? Okay, well, you would clearly here, you would start with benzoic acid. And so here, wait. Let's just write it down. So we have, so what we want to start with is benzoic acid plus methyl magnesium bromide. Okay, part B. Ooh. Oh, wait, actually, I got it. This one's easy. All right, so we're going to start with ethanol. Or wait, we're going to start with ethanoic acid, maybe? Ooh, is that right, though? I think that's right. And then we're going to do phenylmagnesium bromide. Yeah, so the Grignard reagent is phenylmagnesium bromide, and the base is acetic acid. I mean, you just look for the substituent. So here, 1, 2, 3, 4, 5. So we're going to start with, so C is going to be pentanoic acid. And then it's also going to be ethyl magnesium bromide. So look and see if I'm right. Yeah, methyl magnesium bromide, phenyl magnesium bromide, and oh wait. Does it need to be an ester? Is there a reason it needs to be an ester? So it really should be R benzoate, and it should be um, R acetate, and it should be R pentanoate. R pentanoate. Okay, that was a good stumble because you cannot just use a carboxylic acid, like I said. You have to use an ester. That's also why water, you can't have any water in Grignard reactions. Easily accessible protons will just kind of destroy the Grignard reagent. But let's see, I got everything else right. Ethyl magnesium bromide. And then R pentanoate. Okay, good. That was kind of a doozy of section, man. Esters were long, bro. But it makes sense, all things considered, to spend that much time on esters and all of this stuff, but it's like kind of a slog. Just how much material it is. Amides, like esters, are abundant in all living organisms. Proteins, nucleic acids, and many pharmaceutical agents have amide functional groups. The reason for this abundance of amides is that they are stable in aqueous conditions found in living organisms. Amides are the least reactive of the common acid derivatives and undergo relatively few nucleophilic HCl substitution reactions. Yeah, amides are the bottom of the pool. Even I've been doing OChem for like 2 quarters now, and this is okay, kind of, to understand. I see the amide bond here. But then this, even I'm like kind of glazing over. But actually, it's just because this weird four-membered heterocycle, like benzyl, dude, like this molecule is just weird. Like all of this is okay, but then this crazy stereochemical mess that happens here is like freaking my mind out. And then here, I think it's just because I am familiar with it from other contexts that I'm like, what the hell is going on? All right. Preparation of amides. Amides are usually prepared by reaction of an amine with an acid chloride. Ammonia, monosubstitute, and disubstitute amines all undergo the same reaction. Reaction. Okay, so that's that's basically it. Hey, you want a amide? Use an acid chloride. You want amide? You use acid chloride. Reactions of amides. Conversion of amides into carboxylic acids. All right, hydrolysis. Amides undergo hydrolysis to yield carboxylic acids plus ammonia or an amine upon heating in either aqueous acid or aqueous base. The conditions, I always love that when the reaction can go either through acid or through base. There's another really cool example that I can't remember now. Really, I feel like if you wanted to understand OChem, or at least if I personally wanted to understand OChem, I would kind of have to do this book twice. Like, there's just so much content. Amides undergo hydrolysis to yield carboxylic acids. The conditions required for amide hydrolysis are more extreme than those required for the hydrolysis of acid chlorides or esters, but the mechanisms are similar. Acidic hydrolysis reaction occurs by nucleophilic addition of water to the protonated amide, followed by transfer of a proton from oxygen to nitrogen to make the nitrogen a better leaving group and subsequent elimination. All right, an amide is reacted with acid, protonates the carbonyl oxygen, making this much more electropositive. The water then attacks this electropositive electrophilic carbon, pushing the pi lone pair and the carbonyl up onto the oxygen. Now we have this oxonium, which does a proton transfer to form a positive nitrogen. Okay, and then now water takes a proton. And you see there's really, I mean, proton steps, you see that there is relatively high. And this is another thing about chemistry that I wish people said more, I think. My feeling is that there's a ton of different orderings by which the proton transfers could happen. And my feeling is this is another case where you have you're under representing the level of dynamism by drawing a specific mechanism and saying that this is how this works. I think the impression that a lot of people, including me, get is, okay, this is the order and this is how it has to happen. But like, is it really? I don't know. I'm not like totally convinced that this is always the way that it happens, that water takes this proton and the electrons flow into a carbonyl, which then causes the elimination of ammonia. You know, so maybe I should just. A problem that I have with organic chemistry is that when they draw these mechanisms, typically there's a number of different ways in which the order of the proton transfers could happen. So, you know, like for instance, the mechanism that's drawn in the textbook says, okay, water takes this proton. But is it really always that case? Or is this a case where the textbook basically is underreporting the level of dynamism and variability in what's actually happening in the flask? And it's just one story of many, and maybe possibly the major story, you know, like the major product. It's probably maybe mostly what happens, but there's in reality, a large variety of things that happen to actually form some product. I mean, it's just going to confirm my beliefs, which I feel pretty confident about, but it's like, textbook mechanisms massively compress the actual molecular chaos in the flask. Yeah, like I would be curious to know how you could actually probe at like, and the question would be like, is it even valuable? Of course, I would say yes because it's interesting. Like, how do we get at the truth at what is really happening? But it does seem like a pretty difficult problem to to get at. But okay, so what are we doing here? You know, if I had to characterize this, it's the formation of a carboxylic acid from an amide. So it's hydrolyzing an amide. So amide hydrolysis. This is an interesting last step though, because that shows that like you, I don't know, they may be biased towards carboxylic acid. Basic hydrolysis occurs by nucleophilic addition of hydroxide to the amide carbonyl group, followed by elimination of the amide ion and subsequent deprotonation of the initially formed carboxylic acid by ammonia. Amide ion is a very poor leaving group. Okay, so yeah. Amide hydrolysis is common in biochem. Just as the hydrolysis of esters is the initial step in the digestion of dietary fats, the hydrolysis of amides is the initial step in the digestion of dietary proteins. The reaction is catalyzed by a protease enzyme and occurs by a mechanism almost identical to what we saw for fat hydrolysis. That is, okay, I'm not going to look through this. I mean, it's kind of interesting, but okay, we have there's some enzyme with a boom. Hmm. Hmm. Okay. That's pretty cool, I guess. All right. Conversion of amides into amines by reduction. Like other carboxylic acid derivatives, amides can be reduced by LAH. Switch over. Um, what the fuck? The 144 hertz or the 120 hertz is so noticeable, dude. I love 120 hertz. It's so much better. Okay. Like other carboxylic acid derivatives, amides can be reduced by LAH. The product of this reduction, however, is an amine rather than an alcohol. The net effect of an amide reduction is thus the conversion of the amide carbonyl group into a methylene group. Wait, what? Here's the mechanism. Amide reduction occurs by nucleophilic addition of a hydride ion to the amide carbonyl group, followed by the explosion of the oxygen atom as an aluminate anion. Wow, that's so weird. To give an iminium ion intermediate. Oh, that's so weird, dude. Okay, we gotta write this one down. This is actually so weird. This is one of these ones that's like actually different for once. The reaction is effective with both acyclic and cyclic amides or lactams. So a lactone is a cyclic ester. A lactam is a cyclic amide. That's cool. Is a good method for preparing cyclic amines. Why? Oh yeah, because you can just do that. How would you prepare N-ethyl aniline by reduction of an amide with LAH? Oh, I don't want to look at the answer. I think it would have to be that this has, wait. The double bond has to be here. The double bond can't be here. The double bond has to be here. Boom. I promise I didn't look. I knew it. How would you convert N-ethylbenzamide? Okay, so first off, there we go. N-ethylbenzamide. Okay, so first off, benzamide. So we draw benzoic acid. Then we stop at the second O, and we write N, and then the ethyl group, and then H. How would you convert this to the following products? Okay, so we want to make this to benzoic acid. So we are reducing an amide to carboxylic acid. So presumably we want hydrolysis. So I'm going to guess that the answer is just H3O plus. And basically what happens is this thing gets protonated. Then water comes in. Then something like water comes in and takes this proton. And this swings into the carbonyl and kicks off this. Or it's actually probably even more possible that before that even happens. Well, yeah, before that even happens, we say that like H2O comes, takes this proton, and then another H3O comes, and nitrogen comes and takes it. So then we get phenyl. Then H2O comes, takes this proton, this flows in the carbonyl, this kicks off the nitrogen, and we're left with all right. So I think the answer is acid because I can see a pretty clear route to how we got that. Now we want benzyl alcohol, which I still don't know how to name. I remember what it is, but I don't know how to name this thing. And we want to make this from N-ethyl benzoate or benzamide. N-ethyl benzamide. So how are we gonna do this? Oh wait. So what we're taking an amide to just a primary alcohol. I don't know if we need more than one step, but we could, because the thing is, if you react a amide with LAH, you get an amine. And I think amine is not what we want here. But if we did do Grignards, can we do Grignard on this thing? Because the obvious route for me is you turn it into a carboxylic acid with hydrolysis. Now, once you have a carboxylic acid, you can just normally reduce it with LAH. So I would say 1 H3O, and H3O does what? Hydrolysis. Then 2, we want to react it with LAH to take the Ca to a primary al. But the thing is there a better way? We know we can't just directly react it with LAH. Because reacting LAH with an amide gives an amine. That's what we just said. This is a good one. Is it more obvious than I thought? Do we have a Grignard thing? We have hydrolysis? Okay, I'm gonna go with what I have. Let's do the last one, and then I'll check the answer. All right, so this looks like a phenyl group. CH2. Okay, wait. This isn't this? This? I'm pretty sure that is. Oh, but it's not exactly. It's a little bit different. We have NH and then ethyl. And then there's no oxygen whatsoever. So here we have an amine, right? So we know that if we want an amine, we're going to have to use LAH. I mean, I think we could probably just... Oh, but we have to start from this. Oh, yeah. We literally just... We have that. So all we have to do is reduce it with LAH. That's it. Okay. All right, let me do this one. Or I'm at the end of the page. I'm going to do this. Oh, wrong one. Okay. Okay, this is part C. Part A, you just add acid, which is what I said. Part B. Oh yeah, I think you do need water. Or some sort of thing to protonate. This one's weird though. I don't know what BH3 is. I feel like it was in the chapter, but there was so much that I can't even remember. I don't know. Whatever. It's fine. I can figure that one out later. All right, so this one I'm probably going to just kind of glance at because it's time to now move to the problem set and my teacher's notes, maybe. Okay, how would you use the reaction of an amide with LAH as the key step in going from a bromocyclohexane to NN diethyl or dimethyl? Dude, this is what I'm saying. It's like a UPAC is just bad. NN dimethyl ammonia. Oh my gosh. Dimethyl amino methyl cyclohexane. All right. Well, I already got the hint that actually, I don't even remember enough of it, so it's still gonna be a pretty good problem. Okay, let's try to do this retrosynthetically. We know that if we add LAH to this, that then we're gonna have psi. Let's just draw it. So there's this O N. Here we go. Oh, wait. Hold on. Can you have this? This would be interesting. I never thought about this. You could have an acid chloride amide. Is that allowed? Because if I did that, then I could totally see how this thing happens. Because then I could use my cyclohexylphenyl, what the hell? Phenyl magnesium bromide, cyclohexyl magnesium bromide. And this comes in, and then oh wait, this isn't even meant to have the. All right, how do you do it? Because that's the only thing I can think of is how this thing happens. Oh, that's so clean. Oh, this is actually one of those like I don't know why. Sometimes the questions here they vary in difficulty so much. Like I wish. Okay, wait. So there's something important that I forgot, which is if we have a Grignard, we can react it with CO2. And what happens? So then we have. And I think, do we just add acid? Is that what happened? Okay, yeah. So this is like one CO2 in ether, I guess. Two H3O plus. I would love to do some reactions with carbon dioxide. I mean, that's really cool stuff. Yeah. So this comes takes this proton, and now we have. And now we have cyclohexane carboxylic acid. Once we have this, we can add SOCl2, which is thionyl chloride, and that gives us cyclohexoyl chloride. Wait, no. Okay, so the original thing is called cyclohexane carboxylic acid. Super long name. Now we want to name the acyl group. And the acyl group should be called probably cyclohexane carboxyl. No, it's probably cyclohexane carboxyl. So then I'm going to call this carboxyl chloride. What is the chloride called? Chloride acid derivative called cyclohexane carboxylic. Yeah. Oh, it's called. Oh, okay, okay. It's called cyclohexane carbonyl chloride. But that's one of those ones where I'm just like, you know what? That's a niche rule. I don't really feel like I need to memorize that. Okay, but then once we have this, we can now react a chloride. I mean, acid chlorides basically react with everything. So my feeling is that then I can just do uh, the what is it called? Dimethylamine. So then we react this with. So what happens in this thing? I'm pretty sure that this thing is already electropositive enough to come up here and do our whole dance. And so then we get. That was a really good problem. What a bang. Oh, wait, but yeah, so then finally LAH to make the amine. That's a hard problem, dude. There's a lot of steps to that one, man. I'm just gonna skip this. I would love to go into it, but it's not really in the cards right now. Same with this, I think. Polyamides and polyesters. Step growth polymers. When an amine reacts with an acid chloride, an amide is formed. What would happen though if a diamine and a diacid chloride were allowed to react? Each partner would form two. Oh, I get it. That's fucking cool, man. There are two main classes of synthetic polymers: chain growth polymers and step growth polymers. The polyethylene and other alkene and diene polymers that we saw in chapter 8 and 14 are called chain growth polymers because they are produced in chain reaction processes. An initiator adds to a C double C to give a reactive intermediate, which adds to a second alkene molecule to produce a new intermediate, which adds to a third, and so on. By contrast, polyamides and polyesters are step growth polymers because each bond in the polymer is formed independently in a discrete step, often the nucleophilic acyl substitution reaction of a carboxylic acid derivative. Some commercially important step growth polymers are shown. Hexamethylene diamine. Why is that named so weird? Oh yeah, bro, come on. This name is just so much better. 1,6-hexadiamine. Or hexane 1,6-diamine. All right, yeah, methyl hexamethylene diamine. That's a stupid name. That's so cool. A 9010 copolymer of polyglycolic acid and polylactic acid is used to make absorbable sutures. The sutures are entirely hydrolyzed and absorbed by the body within 90 days after surgery. That's pretty freaking cool, bro. Alright. Alright, so that concludes, I'll probably do some review and some problems. But hopefully there's a lot of problems. I think dude, carbonyl chemistry is like huge topic. See, I wish the files thing was actually better. That's not so bad. Yeah, the first week is carboxylic acid. Actually, to learn about carboxylic acids in a week is pretty nuts. Damn, we have a midterm. Yeah, this class is gonna be intense. 6 weeks is actually pretty intense, man. I'm gonna be studying a lot. Okay, but that is it for now. See, 220. That's pretty good. Yeah.